So we will start with organic chemistry, and this is your next class for organic chemistry part 1. I have already posted the IUPAC rules document on Blackboard, so you can read it before we start with naming the organic compounds. So regarding the organic chemistry and your book, unfortunately, your book doesn't have that many organic chemistry problems. As many problems as I can find, I will post it over here, but most of my problems I found from other internet resources or from other books that I used before. It's not difficult to find more problems to practice, but I will also create a practice test for you on Blackboard so you can solve some problems on your own before you start studying for your next exam. So let's start with organic chemistry. What is the organic chemistry? Organic chemistry is defined as the chemistry of carbon-containing compounds. So most of these compounds do come from living things or other things that we were once living, but some do not. Perhaps the most remarkable thing about organic compounds is their sheer number. Of the tens of millions of known chemical compounds, more than 95% are actually compounds of carbon. And why is it very important that we learn about organic chemistry? Is that the question is number 1. List 3 characteristics of the carbon atom that make possible the existence of millions of organic compounds. So one reason for the huge number of organic compounds is the carbon atom itself. Carbon is unique is that its atoms bond readily to each other and form long chains. So as you can see, carbon atoms can form chains. Carbon chains can also have branches or form rings of various sizes. This is another very good characteristic of carbon atom. And the third one is that the same carbon atoms can be arranged different ways, and it's also called isomerism. And the question 2 is actually what are isomers and how can you tell whether or not two compounds are isomers? Isomers are molecules that have the same number and kinds of atoms but different structures. And over here I provided to you some of the examples of isomers. It is very easy to find an isomer because, for example, over here we have an isomer of pentane. And we have different structures over here. I hope it's not going to scare you. The top 2 isomers are representative of skeletal structure, and the bottom 2 are just the structural formula of pentane. As you can see on the skeletal representation, there are no carbons or hydrogens. And on the bottom, where the structural formula is, you can see all of the carbons attached to hydrogens or other carbons in the structure. And as you can see, all of these molecules contain 5 carbons, and therefore they're all pentane isomers because the number of carbons and hydrogens are the same in all structures, but the location of carbons is different. So, for example, on the bottom you can see the structural formula of pentane. This is the most common pentane, right? So you can count 1, 2, 3, 4, 5 carbons. Right next to it is also an isomer of pentane, but the name for this pentane is going to be different. We see the same 5 carbon atoms, the same amount of hydrogens in the structure, but the name is going to be different. The name is going to be 2-methyl butane. As you can see in the structure, you say that it's a butane, but then you have an alkyl group that is methyl attached, and in total it has 5 carbons. The next structure is a little bit different. It is The longest chain over here is represented with 3 carbons, 1, 2, 3, and there are 2 attached alkyl groups, which are methyls because it has only 1 carbon on the side. But when you add all the carbons and all hydrogens, the formula is going to be the same. It's going to be C5H12, which is the formula of pentane. So this is, all these structures are representatives of isomers. Question number 3. Which of the following compounds are organic? So in addition to carbon, almost all organic compounds also contain hydrogen, many contain oxygen and or nitrogen, and quite a few can contain sulfur and halogens. Halogens are the nonmetals that are, for example, like chlorine, bromine, iodine, and so on. Nearly all the common elements are found in at least a few organic compounds. So among all of these examples, A, B, C, D, we can find some of them that are organic and some of them that are actually non-organic. How will you define it? So all organic compounds must have carbon in their structure. Compounds that do not have carbon in their structure, meaning are not organic. So let's look at example A. C8H18O. We have all possible organic elements: carbon, hydrogen, and oxygen. Therefore, this compound is organic. Let's look at B. So don't make sure you know all of your elements. Please refer to the periodic table if you don't know what kind of element it is. But as we can see, there is no carbon in the structure, therefore it's non-organic. The next example is C. We have hydrogen, we have carbon, and we have sulfur. We have carbon in our structure, the most important, therefore it's organic. The example D has no carbon. Please do not confuse CO, which stands for cobalt, or CO, which stands for chlorine, not carbon and iodide. This is CO. Make sure that you understand which element is which. So therefore, this compound is non-organic. Okay. So we'll concentrate on the most important, most basic naming of all of the alkanes, alkynes, and alkenes. The simple structure, carbons today, and then we'll proceed to the more complicated. That's why there's going to be part 2. For this type of question, how many carbon atoms are there in the molecule of each of the following? You'll have to memorize this table. This is something that will follow you throughout the whole organic chemistry, and this is the parent name for all of the organic compounds. So if it's 1 carbon in a structure, then you know it's methane. The parent name is meth over here, and then the suffix will change if you have a different type of structure. So this is the representation for alkanes, compounds that have only single bond between carbons. There's also alkenes that have a double bond between carbons, and there's also alkynes that have a triple bond between carbons. And therefore, if you have something with a double bond, the suffix "ane" will change to "ene", and if you have something with triple bond, the suffix "ane" will change to "wine". So it will be, for example, if 1 carbon, but there it cannot be that way. So if it's 1 carbon, it's always going to be methane. If there are 2 carbons, it can be ethane, it can be ethene, or it can be ethine. Okay, so you know the prefix, the parent name. This is the first one: methane, eth, prop, bute, pent, hex, hept, oct, non-deck, and the rest is a little bit more complicated, and usually you cannot see them. You're usually not going to see them, but this is going to remain the same for all of them. So let's start with the question. How many carbon atoms are there in a molecule of each of the following? You look at the name hexane and you refer to your table and you can see that hexane has 6 carbons and you write 6. B asks you for decane. You look for decane and it's 10 carbons. This has to be memorized and you cannot have this table during your exam, but you have to make sure that you know and you quickly determine which one is which. So let's look at let's move on and we'll remove the table and we'll just try to determine. So problem number C says that this is a cyclopentane. I hope that cyclo is not going to confuse you, because it doesn't matter if it's actually cyclo or just pentane. You know that there's pentane, and pentane has 5 carbons, therefore it has 5 carbons. Cyclo is just representation of the shape of the molecule. That's it. D, it says that it's 2-pentene. So this is a little bit tricky because we haven't started this naming yet, but as you can see, the parent name is pent. Therefore, you know that parent name is pent. Therefore, you know that there are 5 carbons. The suffix "ene" represents that there is a double bond, and number 2 shows you where is the double bond located. It is located at the second carbon. Okay, so next one is ethane. This is very easy. This is a regular alkane and it has 2 carbons. Example F is talking about propine. So the parent name is prop, right? And wine is just the suffix, just to let you know that there is a triple bond. But what we are looking for is the number of carbons. So you know that there's prop. This is 3 carbons. Cyclobutane is the same as we had with the cyclopentane. Cyclo means just the way the molecule is shaped. It means it's cyclic, it's in the shape of a square. And butane means that you have but means that you have 4 carbons. Ane means that you have only single bonded carbons, and cyclo means that it's in the shape of a circle or cyclic structure. Okay, question number 5. Write the molecular formulas and condensed structural formulas for the two examples. So this is pentane and nonane. You have to make sure you know how to identify what is the molecular formula, what is the condensed formula, what is the extended formula, and what is the skeletal formula. So molecular formula always counts all of the carbons and all of the hydrogens. And there is a formula for each one of them. So for alkanes, alkenes, and alkynes, it is very easy to find the formula if you know the number of carbons in the structure. So the formula is going to be the number of carbons. For hydrogen, it's going to be the number of carbons multiplied by 2 and plus 2 extra. So if we can see there are 5 carbons, 5 multiplied by 2 is 10 and plus 2 more is 12. For C9, it's going to be 9 multiplied by 2 is 18 and 18 plus 2 is going to be 20. So this is how you can figure it out. You can also probably look it up if it's easier for you. So let's write with the molecular. Molecular is usually, like I mentioned before, is all of your carbons and hydrogens. Condense is when you write all of your carbons and all of the hydrogens attached to it. So you do not show the bonds with the lines for each hydrogen. you're just condensing them. So the first carbon will have 3 hydrogens attached to it. Remember, carbon makes 4 bonds. So